Cool. So welcome to the fifth week of the Quant University Fall School. And we are very pleased to have Stephen Jansen, CFA, who is going to be presenting on synthetic data generation. I'm a big admirer of your work, Stephen. And it's also a pleasure to kind of see someone who is not only kind of having the experience in the financial services, but also has taken time to author a wonderful book and sharing his knowledge on how do we actually implement these technologies. And as we mentioned before, synthetic data generation is something which has taken the industry by, there's a lot of intrigue about like what synthetic data generation is and how do we actually implement these technologies. And with generative adversarial networks and VAEs and deep learning and a lot of different methodologies, the traditional statistical methodologies of forecasting has been augmented with some of these newer methodologies. So we would love to have Stefan talk about like how do we think about synthetic data generation, and Stefan has really put a lot of time in putting together a very good example on his GitHub page. And we have had the pleasure of putting that on the Q Academy. So I'm going to share a couple of things before we get started. For people who don't know us, we are Quant University. We're based out of Boston, and we are focused on the intersection of data science, machine learning, and quantitative finance. We have done a lot of work in the industry, and also since COVID-19 hit, we have been taking these workshops in an online mode, and we have consistently had more than 15 sessions on various themes and topics, primarily the intersection of data science, machine learning, and quantitative finance. And we have, this is the fifth lecture of the series, and we have many more lectures to come, focusing on machine learning, scalable AI, governance, and some fintech-related topics. And we are also now gearing up for the winter school, and we are offering many courses. One is a data science course, machine learning course, a model risk management course, synthetic data generation and stress testing course, fintech bootcamp, anomaly detection. So if these are topics of interest and you're planning to augment your knowledge, please do consider applying to the qwinterschool.splashthat.com, and we will share more details as it becomes available. So without further ado, I'd like to introduce the speaker of today. Stefan Jansen is the author of the book, Machine Learning for Algorithmic Trading. And it's one of the best books I've read in the context of implementation and how do you actually take these concepts and then apply it in practice using Python. And Stefan is not only an author, but he has a company called Applied AI, where he consults with various Fortune 500 companies and builds end-to-end machine learning systems. He has a lot of experience working at fintechs, large banks, including the World Bank, and has a rigorous background. He's got a computer science background and also economics background, and he's also a CFA charter holder. So it's an absolute pleasure to have you present at our fall school here, Stefan. And I'm going to stop presenting and make you the presenter, and you can share your screen now.
Excellent. Thank you so much, Sri, for having me and for the kind intro. Let's move over to my screen, to the browser where we have all the good stuff. Thank you, everybody, for joining. So you should now be able to see my browser with also the presentation up. If you can, just please let me know in the chat. So again, thanks everybody for joining about this presentation, which is really going to talk about one of the chapters in my book, which Sri was kind to mention. Here it is. It's a big book with a bunch of things in there. One of the chapters covers generative adversarial networks and synthetic data. Looks like today you can't write a book without talking about these things. I noticed some folks in the audience that I've interacted with around the book in the past, so you're a special welcome. Everybody else, of course, encouraged to take a look at the content of the book. There's a website for the book at ml4trading.io that has, lots of chapter summaries and also links to the GitHub repo that has around 150 notebooks that cover a bunch of different topics from how you get the data, how you generate or create different machine learning models to create predictive signals and backtest strategies that use these signals to hopefully produce a profit in the end. And there's a part on natural language processing. And then in the end, there's 6-7 chapters on deep learning, which is what we talk about today, about one of them, right? So to get up to speed quickly here, I'll very briefly introduce generative adversarial network. I'm generally assuming you've heard this before, so it's more like a quick reminder. And then move on to the topic of the day, which is why would synthetic data be helpful for finance, and then more specifically, how could we actually generate them? So I'm going to replicate a paper that was presented at NeurIPS last year that uses an interesting new type of architecture that's somewhat complex, but interesting because it really focuses on reproducing the stepwise transitions that autoregressive time series tend to exhibit. And we'll see how we can implement this in TensorFlow. And then we can also take a look at how we could evaluate the results produced by such a network. So let's get started. I would encourage you to throw any questions you may have throughout in chat. I'm looking at it occasionally, so please don't hesitate if anything is unclear or if I'm speaking too quickly or the other issues, just bring this up right away. So generative adversarial networks, of course, have been all the rage for the last 5-6 years. Ian Goodfellow came up with them in 2014, of course, with some co-authors. As you've seen on the previous slide, Jan LeCun was very excited by the idea. And the idea is, as you can see in the architecture below, to have two networks compete so that one network learns to generate samples from some population of data in a way that for another web network, it's really not possible to discriminate between a real sample from that population and one generated by this generator network, right? And the fascinating thing is that the generator really learns to do this from random noise inputs, right? So they compete in a sort of game theoretic setting. It's a minimax kind of setup, and they simultaneously train. And of course, there are challenges, as always, with neural network to train them properly, but it has been shown to produce stunning results in quite a few different areas over the last several years. And the initial paper, triggered a wave of research, as you've certainly heard and seen and read probably. I think by 2018, there were like over 500 different GANs that had been published. And you've seen all the results from, the fake images, later fake videos, to the ability to generate other sources of data like music and, images, produce art and the like. So very wide application. And in, I think, 2017, there came an interesting paper that moved into the time series domain and looked at medical data, where data are often very constrained because you have all sorts of regulation, privacy concerns, and the like. And of course, to have more training data in this domain would be a very positive feature. So there was a paper that introduced this recurrent conditional GAN architecture that was able to take in real value time series generated by an intensive care unit, monitor these machines that are next to a patient and measure all sorts of signals and metrics, and to regenerate these types of metrics in a synthetic way, and then train a model on these synthetic data to produce an early warning system that would predict if a patient would enter some specific high alert stage down the road, in the near term or medium term. And that worked surprisingly well, which, of course, made people think which other time series domains could be really benefit from synthetic data. And of course, we're interested in finance. So what about synthetic data for finance? Financial data is also somewhat scarce, especially if you compare it to the web scale domains, with the cats on YouTube and the IoT sensor data and the like. Clearly, financial data, even though the frequency may be high, there's a limited number of instruments that are being traded worldwide, and the history is what it is, and it's not growing exponentially as in other areas. So this sort of limited pool of historic data clearly, create some constraints when it comes to designing models, training models on these data to predict, returns or the like in the future, and also to backtest strategies. So wouldn't it be great if we had a way to sort of create an abundant or unlimited set of historical time series data for subdomain or investment universe of our interest, and simply use that to augment the data that's available, right? So that would be really awesome. Maybe we could do this for specific regimes. We could do this for specific sort of volatility regimes that are in place, or simulate more data for certain historic episodes that we would like to backtest our strategies on, and so forth, right? So is it possible to do this? And of course, maybe it's not. Maybe time series data is very special in finance, the market dynamic and sort of all the pattern that creates. Maybe it's just so much harder. So maybe we have to try, right? And thankfully, some have done so. So in 2019, so last year, Jingsun Yoon and co-authors from University of Cambridge, Yoon himself is now at Google, came up with a time series GAN that enhanced on some of the architectures that have been discussed before. And the goal was to specifically focus on creating a model that, as it generates data, synthetic data, that these data really reflect the temporal dynamics, so the transitions from time step to time step, both across time and also between the variables, right? So essentially look at sort of the large correlation matrix that exists and try to replicate these patterns and relationships as it comes up with synthetic data. So, and what's new in this architecture is that it does not only use an adversarial process to generate a discriminator to figure out if certain time series match, the real samples, but it also uses an unsupervised autoencoder that uses an embedding space to create samples, and it adds a supervised loss that makes sure that the generator also incorporates the patterns that are observed in the real data from time step to time step, right? So you can already get a sense that we saw this basic architecture here with two networks, which already is somewhat complex. Now we will get a new beast that is a little sort of a step up. And here you can see the architecture visualized, where you see that we now have two networks with 4 components. So now we consider the adversarial networks, which has the generator and the discriminator, as one network. And then we have an autoencoder on the other side, so on the left side, that produces embeddings to project the time series samples into a latent space. And as it does so, there's a supervised loss that constrains or disciplines the generator to produce samples that match the transitions and the time series patterns that we see in the real data. So the logic there is that it may not be enough to simply generate time series and then compare the overall loss between the different time series, but to actually also make sure that at each and every step, we kind of follow the ups and downs and the sequences that we see in real data. So that's kind of the assumption and the logic that the authors apply. And thankfully, they made available some sample code in TensorFlow 1. And the contribution in the book is that I basically poured the TF1 to TF2, simplified as much as possible so that it's relatively accessible and easy to not only follow along, but also to build on, right? So just like the other things in the book, it's basically an encouragement for you to kind of take what are often simple approaches and contribute to your own creativity to build them and improve them. But also see in the example that we look at now that the authors use, among several examples or experiments that they run, they use one example with stock price data where they use the open, high, low, close, and volume data for one stock series. I use 6 different stocks with daily closing periods. But other than that, I very much follow their implementation, the setup of the architectures, the training parameters, and the like. So it's not specifically optimized for this slightly different use case. So if you want to look at the code, then you have two options. As we mentioned, on Google Colab, you have something that's ready to run. And if you want to get it from GitHub, there's a new repo that I created that is very similar to what's on the book repo part for chapter 21, but it has much additional commentary. So it's basically the chapter 21, the parts that are relevant, they are included in the notebooks. So here it is. Oh, let me go back up. So here we are at the first notebook. So there are two. We're going to look at how to implement the notebook. How to implement the architecture and to train it. And then we, in the second notebook, are going to look at some techniques that the authors use to evaluate the quality of the results, right? Because you still need to somehow take a look at it, decide, is this actually good enough for whatever objectives I have? So we see three examples of that. All right, so now we're ready to dive in. So you see there's more commentary than in the original notebook, links to the original code, the paper, and the like. I really encourage you to read the paper if you're really interested in the subject matter. I'm skipping over all the mathematical notations. You'll notice down low that there are several variables with somewhat funky names, and all these names are, taken or to follow the notation that the authors use in the paper, right? So you can compare the equations and the logic, how the authors derive their approach and get from the initial assumptions to their training and loss functions so that you can kind of follow along. So after the intro and loading the data and setting the path, right, we're going to start designing. First, we're going to get the data, and then we're going to design the architecture, right? So to repeat, because it's important, the goal of TimeGAN is to really ensure that we generate time series that not only look the same sort of high level, but that also on a time step by time step basis exhibit dynamics that we find in real data. And we do this by using supervised learning to basically have an autoregressive process that penalizes the generator if it doesn't really obey what's present in the real series. And that again leads us to these four components, with the two different networks that I just mentioned. And here you have more text if you want to revisit after that. This explains the different components, right? All revolves around this latent space that is conditioned to proceed according to the temporal dynamic observed in the source data. Now, to make this work, so that the networks actually learn these dynamics and are able to generate realistic data, we need to jointly train them, and we'll do this in three phases. So we first need to train the autoencoder, since everything revolves around the representation of the time series that is learned by the autoencoder and used by the generator. And then we're going to train the supervisor, because later in the third phase, where we train sort of everything together, we then use the supervised training of the generator in sort of alternating steps with the traditional GAN training, where the discriminator interacts with the generator, right? So there are three phases. The third phase is much longer. If you run this at the 10,000 steps that the sample uses in the original notebook, you'll see that it takes about an hour to run with the GPU. Okay, so high-level setup should be clear now. Two different networks with two components each. Things revolve around the latent space in which we project the time series, and we train in three phases to get the different pieces sort of up to speed as we need them for the joint training, which is sort of the centerpiece. So we need to now do this in TensorFlow 2. So there's a few steps we need to follow, which is, of course, get our time series inputs, make some decisions about what kind of sequences do we actually generate, how long should they be, how many time series should they contain, and so forth, and then create the architectural inputs, and then the loss functions to kind of set up the training, then actually run it, and then see what we actually get out of this. Good. So now the data uses as much in the book, it relies on this Quandl wiki prices data set that has end of day close prices, but also open and so forth. including adjustments. Unfortunately, it ends in 2018 at some point, but nonetheless, it gives us for some stocks quite a bit of history. And to keep it simple, I use 6 different stocks from this data set that had a longer history. There's no specific analysis has gone into why I picked those stocks. Having enough data was kind of the main criteria, right? So we have Boeing and Caterpillar and Disney and so forth. So that's kind of the input, right? So we have a long time series, relatively long, with 4,500 observations starting in 2000 and running until the data set was no longer maintained in 2018. So there's a few parameters, right? So the choices I mentioned, how long should the sequence be? So we're going to generate sequences with 24 time steps, and we're going to, follow the pattern of have 6 parallel time series in the sample, and we need to set the batch size for training. We're going to use 128. These are the original data, right? So we normalize them so that they start at 1, and so you see kind of different, more or less successful stories unfold over time, and you can also see the correlation between them. Some are highly correlated, others are not so much. So there's a bit of diversity in there, right? Be clear, this is a small data set, right? In a real application, you might be interested in using more inputs. Of course, with that would come more training effort, changes to the architecture, and so forth, right? So this is a relatively, not exactly a toy data set, I'd say, because it still covers some 18 years, but for a sort of, an application that aims for production-ready data, you would probably want to scale things up a little bit. We're going to scale the data, so we use the min-max scaler, so it's in the 0-1 range, and then we're going to create rolling window sequences that are 24 steps long and have an overlap, right? So simply roll this forward by 1 step each time, which gives us some 4,500 or so sequences in total, and we're going to convert those to TensorFlow data sets, so it's easy for the network to utilize them. Now, of course, we need to generate random data, and here we're going to use uniform data that are independent of each other over time, and this is also going to then be available as a TensorFlow data set to the generator, which receives that as one of its inputs. Good. So now we're going to start defining the GAN itself, and we keep it relatively simple. You could, of course, think about the architecture for each of the different networks. In this case, we simply use recurrent neural networks, and in a minute or sooner, define a function that automatically creates these units that consist of gated recurrent units. So we're going to use hidden dimension of 24 units. All of the networks are going to have 3 layers, and that's basically following what the authors did. Again, in practice, you obviously would want to optimize this, and especially if you use more data. Relatively simple function that produces the standard autoregressive RNN block for each of the different components. The only network that's a little shallower is a supervisor that uses only 2 layers. So they get their 3 layers of the given hidden unit size, given number of outputs, depending on where they sit in the architecture. So that varies using sigmoid activations here. And then we just generate them, right? So there's an embedder and a recovery. So that's the autoencoder pass with its 2 components on the one side, 3 units each. The embedder, produces, projects things into a space with 24 hidden, 24 dimensions, and the recovery projects it back or recovers it to the original size. So that's the first part, and the second part is the adversarial network with the generator and the discriminator, and a supervisor that we use to discipline the generator to obey those temporal dynamics. So again, using the same make RNN function and creating the networks with specific input and output units we want. The discriminator has only one output because it decides whether the output is true or false, or real or synthetic. Good, then we can proceed to the training steps after we define the requisite loss functions. So we will train this for 10,000 steps, or I think 3 online was a little more gentle on your time commitment and reduced it to 100 steps. So you can see how it works. And of course, if you have more time, you can use more steps. There are a few hyperparameters in the network, I guess gamma and others that that weigh different losses relative to each other. So you can look into the paper what they all are for, because since you have several losses, in some cases you need to combine them. So there are questions on which weight should you give each loss, for instance. They also say they don't find like a huge impact of these hyperparameters and propose some sort of baseline values, which I'm using, but the paper reveals all the details. There are multiple loss functions. They use as inputs the mean squared and binary cross entropy, then with some additional computations. So we define some basic building blocks here that we use. And then we move on to actually define the architecture of these different networks with their various components, right? So the autoencoder has the embedder and the recovery part of it. And here you see it projects this into actually not necessarily a reduced space, which here is also a result of using relatively small data. So use this block of 24 by 6 sort of time series block projected into a 24 by 24 space. So that's one change here. But you see overall the autoencoder has around 20,000 parameters, and you also see this visualized below. So that's the autoencoder. If you're familiar with autoencoders, this is just a relatively standard setup using RNNs as building blocks. To train this, we use the embedding loss to guide the training, which uses the mean squared error between the inputs and the outputs, which should resemble each other. And we use the custom gradient tape option in TensorFlow 2 to implement custom training loops, and we use the autoencoder optimizer to define our gradients, which tweak our autoencoder setup to faithfully reproduce the inputs as usual, right? So nothing special here in terms of how an autoencoder is designed. And also the training loop, which here runs relatively quickly, follows a relatively standard autoencoder setup. So this is, if you're familiar again, with autoencoders, nothing very sort of special happening here. So then we got the supervised training. So that's phase 2 before we jump into the sort of joint training where all parts become active. And here we essentially train the embedder. So that the embedder provides the input. So we're operating in this latent space, and the supervisor receives these inputs, and we compute the loss. So to ensure that the input or the representation in latent space follows over time the patterns observed in the real data. And we use this to minimize our supervised loss and apply the gradients to the embedder and later to the generator. All right, so this again is to ensure that the gradient representations, the time series representation in latent space and later in the joint training, the generator obey the time series dynamic. And then, once we have set this up, we follow the training loop, which here is relatively simple in this case, and record the loss. All right, so this is kind of the initial training of our supervisor so that it can be more effective and has already learned some weights as it enters the joint training, which is next. So now things get complicated because now we have multiple loss functions and these various pieces of the architecture interacting. And I'm going to only outline this in a high level. You probably need a little more time than we have today to dive into how all these different pieces hang together, right? So on the one hand, we have a training of the adversarial architecture that is supervised, right? So as I said, the generator is part of the time going to be trained to actually produce synthetic samples that are penalized if they deviate from the temporal dynamics in the real data. So that's what we set up here. And each model has a specific output that then enters the loss function. So here's where you'd have to take out your pen and paper maybe and keep track of the different variables. There's quite a few. So if this is a little much at this point, don't worry. Once you scroll through and especially read the paper, this will all become a lot clearer. Right. So here's one model then. That's our adversarial supervised model. That basically, combines the generator with the supervisor and then the discriminator. And they used iteratively or in alternating fashion in the main training loop. Then we have an adversarial architecture that operates in the latent space. So this again, now you have to keep track of what Z is. Z is the random inputs, and then it outputs the embedded, the synthetic data, but in the embedding space, so in the usually in reduced dimension space, not in the original time series space, right? So it's like we're not producing original images in the normal GAN training, but we're actually producing some sort of dimensionally reduced image to make the training maybe faster, but also to make sure that it follows certain patterns. Then there's another feature in this network, which is an additional loss that can be weighted to which extent you want to incorporate this, which makes sure that the generated data follows certain mean variance patterns, right? Again, you could use different penalties and different metrics, but the idea here is that certain patterns that we see in the time series is also present in the synthetic data. So that essentially measures the mean and the variance in the real data and compares what we get in the generated data. So there's an additional moment loss on the generator that constrains the generator with a certain weight to follow these patterns. And then we have the discriminator. And remember, the discriminator gets, on the one hand, real data, and then it gets synthetic data. And the job is to decide which is which, right? So that's the game it plays against the generator. So the real data architecture simply receives the real time series as inputs, so stock prices. And then there's a synthetic piece where it receives the synthetic inputs from the generator. For all of these, we have different, we have the Atom optimizer, so nothing special. We just need multiple of them because we have different network components that get optimized. And then we have multiple training steps that then executed in sequence as we train the entire network. So there's one step that trains the generator. And then I'm not going to go into detail because it contains all the different components that we just defined. This I recommend take a look at on your own time with a little bit more calm at the paper next to you. The important thing is here that the generator loss down here consists of the unsupervised generator loss on real data and on the embedded data, and it also includes the moment loss with a weight of 100 at this point. All of these are parameters, of course, that you can optimize. And we use this, of course, to optimize the weights of the generator network. Then there's an embedding train step, and then it's a discriminator train step, and ultimately we run all of this in a big training loop, right? So now we sort of bind all of these things together and actually input the pre-trained pieces that we worked on before, right? So there was the supervised part and the embedding part that were already trained during phase 1 and phase 2. And these now join the other components of the network to actually train the generator and so forth to finally produce, hopefully, good synthetic data. And that takes a little bit of time. So this whole training loop with 10,000 steps on a not very current GPU takes around 50 minutes. Of course, you could optimize that with more recent hardware. So we get the different loss values that are produced over time, and we can track those. And ultimately, after 10,000 steps, we arrive at the great moment that we've been waiting for, the last 30 minutes or so, where we see what the generated synthetic data actually look like. So now we're going to produce them, and then we're going to rescale them so we can compare them to the original data. The min-max scaler, of course, allows you to go both ways. And voila. So here's kind of the output that this specific setup gives us. And now it's a little bit in the eye of the beholder to say, well, this is really fantastic. I would not have expected this, or it doesn't really look the same way, right? So I think this is something that's up for debate. Clearly, certain patterns are present. Then maybe they're a little smoother overall, the synthetic data, but the scales roughly match. Of course, the random inputs that the network receives doesn't necessarily align, the real series that have been increasing over time, with the levels of the synthetic data and so forth, But this is kind of what we get. And now the big question is this useful, good enough, or maybe not at all? And that's where we get to the second part, where the authors come up with 3 different ways to evaluate the output. So at this point, and I guess we have Q&A, so we'll have some time to maybe go into some of the details or questions. Also, I want to say, since there's a GitHub repo, if you run this stuff by yourself later, have ideas, feel free to just, put up a GitHub issue. Happy to respond to any questions or doubts, or maybe you find some bugs in the code. So we can certainly interact after this session as well. So now on to the second part, which is, so how could we sort of make sense or answer the question whether this is good enough? And the authors propose, based on, of course, prior work already, 3 sort of criteria. One is actually the generated data diverse enough, or do we have some sort of mode collapse or other phenomena where we may match certain aspects of the time series, but we completely eliminate or overlook other aspects of the time series, right? And for that, we're going to have a visual, which is really like a t-SNE or a PCA plot of both time series to see, how they compare. So that's number 1. Then, to which extent are they actually, fidelity is the name of the criteria. So to which extent are they actually faithful of the input? And there we're going to train a network to train to discriminate or to classify the time series as real or synthetic, similar to the discriminator that we just used in the training process. And ultimately, and I would argue that that's what we really care about, is could actually the synthetic data be used to train a model that actually predicts real data, right? That's kind of where we started with at the outset, and that's what we're going to try to achieve in the end, right? So that's a predictive score where we train a model on the synthetic data and then test it on the real data. So we're going to recover some inputs, get the data back. So, and then we use, first of all, something relatively straightforward. We just project the data into a 2-dimensional space using PCA and the stochastic neighbor embedding, and voila, that's what we get as results. And again, this is a qualitative output, so you can argue, is this really diverse enough? Is it similar enough? Clearly, there is some resemblance between, the output, the synthetic output, and the real series. But then if you look at t-SNE, it also doesn't sort of cover all the wiggles and all the different aspects of it. So it's not necessarily maybe as diverse as the real data, and maybe the smoothness of the time series that you saw displayed, they may be highlighting or reflected here, so that there's some limitation in what we were able to generate with this relatively small example, right? So don't be disappointed, but maybe consider this as a sort of not necessarily a successful proof of concept, but as an implementation of an architecture that maybe gets us some steps towards a useful output. So to get this more quantitative and to get some more harder facts together, how useful this is, we can simply train a model to distinguish between the 2 data sources, right? And then we can do this on the normal train test set approach. So we're going to create, take a certain piece of the rolling sequences to input, and then leave the remainder as a test set. Excuse me. And then would like to see that the network is not able to distinguish between what is true and what is false, right? Because in that case, there would be a faithful representation. So we're going to use, again, recurrent neural network with 6 units, a relatively small unit that network that gets these series as inputs, and that then is trained to use either area under the curve or accuracy to distinguish between real and false data. So we train the data and train the network and evaluate the results on the test data, the test label. And we see that if we look at the test set, that there's a classification error of around 56%, which is almost like flipping a coin, which suggests that the model is not really able to distinguish between true and false result, which is a little not necessarily unexpected, because to some extent that was what the adversarial training was supposed to produce. It's a little odd as the AUC is 0.136. Ideally, we would have 0.5, which would be the flipping the coin scenario. So of course, if you predicted the reverse, there would actually be good results. So I think that's something to investigate a little further, which I actually haven't done. So, but this is the setup how you would kind of say, let's see if, if we train the data on both types of series and train it to predict between real and synthetic data, would it actually be able to distinguish between those on the test set? And it doesn't really look like it can. So in terms of a faithful representation, that seems to be meeting the criteria. And ultimately to what we really care about, which is, so if we take synthetic data as inputs, would that actually allow us to make useful predictions on real data? So we're going to, again, grab our data, get the real data, and get the synthetic data. So we have equal inputs here. And then we're going to select certain subsets of those, randomly picked as usual. So we're going to have some real training data and the corresponding real label. And then we're going to have real test data and the real test labels. So now we're going to have that for real data and for synthetic data. So both inputs and the corresponding outputs, where the outputs is always the last point in the time series. So the goal is you get the first 23 steps of the time series, and the question then is how well can you predict the outcome, the last point in the time series. Again, we use a relatively small recurrent neural network and use the mean absolute error to kind of figure out how good the network performs. From here on, relatively straightforward real and synthetic training, right? So we want to compare how well does the model perform if we train it on synthetic and then test it on real, or if we train it on real and then test it on real. So, and if we go through the next steps, here we ultimately get to the results. So on the left, you have the result if you train the model on synthetic and then test it on real data. And again, the train and the test set. So test set, of course, is a little higher the error. And on the right, you have what would sort of be the baseline expectation if you actually train on real and then also test on real. And curiously, this is on a log scale, the result is a little better, actually. The error is actually a little lower if we train on synthetic data. So important point, though, is you clearly get some benefit out of training on the synthetic data. Right, so that's kind of interesting. You would not necessarily expect that. So this is kind of where we stand with this approach at this point. So there's an interesting new architecture. Maybe let me go back to the presentation because I have some closing remarks here. Right. So what have we done? So we use a paper not developed by folks at finance, by the lab actually works on I think also medical data or bioinformatics. So the idea was to come up with a model that produces synthetic time series data that pays more attention to the correlation between time series at the same point, but also over time. So that was kind of the goal that the authors set for themselves, and they came up with this architecture that uses this interesting representation learning to come up with let's see some. Okay, that uses the interesting embedding space with the supervised sort of penalty, that encourages the networks to follow the timing over time. So then we use an experiment with only 6 stock prices and relatively small series, 24 steps over time and 6 years in parallel to see how well that performs. Mainly a test, though, how can we create the architecture in TensorFlow too, and then what do the results show. And I would say this is certainly not perfection, but it is also not something that would suggest this doesn't work. You know, I think there is quite a bit of potential here because there's of course a lot that you could do to enhance the setup, right? From going bigger to enhancing and maybe creating more specialized architecture. So this was a relatively simple, uniform approach that uses the same setup for all 4 or even 5 different networks components that were part of the training, right? So multiple things that you can do to build on this basic framework, you know, all of which I think justifies pursuing this a little further. And I hope that the material that you have in the GitHub repo encourages you to do so. At this point, with 7 minutes to go, if we're strict with time, I would say maybe we have time for some questions, and I'm also happy to go a little over should there be many questions.
Thank you, Stefan. This was an absolute pleasure, and apologies. I probably took a few minutes trying to get this whole, streaming thing going. We do have a couple of questions, but there were a couple of questions on how do we access the slides. So I'm just going to walk through. Would you mind transferring the host privileges back to me? So if you click the top 3.
Oh, yes, of course. Sorry.
Okay, so I think I should be able to do it now. So when you go into, for people who are new to the Q Academy, basically what we have been doing is the last 15 weeks, we have had various lectures and we're making all of them available for free on the Q Sandbox. So if you go into qacademy.com and if you filter on the topics, and we have the Q lecture series, so you will be able to access all the lectures, the slides, and the associated code. And what we have done is Stephen's code. Stephen shared the GitHub link. You can go directly to the GitHub and get the code from there. Or if you want to access the slides, if you come to the page which I linked on the chat window, you should be able to get the slides. And also, if you say run on Q Sandbox, basically what we've done is we have put this on Google Colab, so you don't have to install anything. You'll directly have a working version of the code, and we've just basically bundled both part 1 and part 2 of the code Stephen shared, and also put the data on Amazon. That way you should be able to run through the Jupyter Notebook without having to install anything. We're just leveraging the Google Colab's free GPU, but in case you're interested in trying it out on your own data with a larger GPU, do let us know, because the Q Sandbox is meant to try out experiments on various aspects, and we'll be able to help you with setting it up so that we can run larger scale experiments. Now, one other thing I wanted to also mention was in order to access it, let me just share the screen. If you go to the page, you will have the various slides, and also at the end, I put in a code, a special coupon code for you. And basically what that will allow you to do is it'll get access to all the prior lectures also. So you should be able to access not only today's lecture, but also the prior lecture. So the code is QUFALL school. So you should be able to try that. So before we go to questions, I just want to let you know, next week, we're going to have Jakob Weinstock, who's also a CFHR holder, by the way. And he was the CTO at a couple of different organizations. We're going to talk about alternative data and access to various aspects of alternative data in the machine learning world. How do you think about different kinds of data sets? So we did have Alexander Daniev and Saeed Amin talk about alternative data in a prior session. We're going to continue the discussion in the next week. So without further ado, I will see if we can talk about a couple of questions. So this was an excellent presentation, Stephen. So one thing, there is a question from Gautier about, would you have time to try this approach on, say, 100+ stocks to see if it captures cross-correlation structures? This is something we discussed when he was presenting too. Do you have any thoughts on that?
I'm interested in making time for this. Then there's real life, which interferes with that. I'm very much interested in that. It's clear that that as you work with the code, you see there are multiple ways to question or maybe improve on how things are being done. Scale is, of course, the first, right? It's 24 time steps, really kind of, the way we should be approaching this. Shouldn't it be 6 series or more? So absolutely, I can promise that I will try so to find the time. So if I do, Gautier, I know, of course, where you are. I think we're connected on LinkedIn, so I'll definitely ping you if I find something.
Absolutely. Perfect. Then Rick has another question. I thought one of the constraints was that the second moment of the synthetic and the real data sets were the same. However, the standard deviation of the closure, everything it's very specific. The code seemed to be much smaller than the synthetic data sets. Was it constraining on the standard deviation of the close instead? Is the question. But I don't know if you want to take it offline, if you have to look at the code and get back to Rick.
Yeah, I'm not exactly, so for instance, this moment loss, I'm also not exactly happy. I'm also not clear if the weights make perfect sense there. So these are all things I haven't investigated, but that's exactly where you would start looking at potential improvements. Because clearly there's some smoothness in the synthetic series that is, not necessarily what we would like to see.
Absolutely. So another question from Sarah. Have you done this on a scale to generate a whole universe of stocks instead of the 6 you chose?
Whether I've done it? Sorry.
Maybe an index or S&P 500 or Dow 30.
Sorry, I didn't. Can you just repeat? Whether I've used a broader universe of stocks, or
I think it's like, can you generate a whole universe of stocks?
So in theory, yes, right? So this is the idea of the embedding space, right? I think becomes even more relevant as you actually scale this up, right? Because we're not using sort of a very complex input here, right? Because it's only 6 time series with 24 steps. The idea of this embedding space is a little bit like the dynamics over time are really only driven by a smaller number of factors. There's actually another topic in the book which talks about this autoencoder paper by Brian Kelly and others from AQR, which also uses dimensionality reduction to identify risk factors in a nonlinear fashion and then does interesting things with those. So clearly, as you scale up the universe of inputs, the embedding space becomes more useful. So the assumption is that you could do precisely that. You could maybe do all commodities, and maybe you could also do others. So, so there's no limitation necessarily. This is more like a toy example, and you saw that even that takes about an hour to run. So you would have to work on the sort of the implementation aspect as well to make this viable. If you go bigger.
Absolutely. Another question is, how does non-stationarity in prices impact generated data?
So the idea is that by capturing these transitions over time, you would sort of be able to incorporate this, right? Because you don't constrain them per se to sort of be limited within that. That's where the mean and the standard deviation aspect comes in, where I'm not sure whether that's the ideal sort of constraint on what we observe in stock prices, right? So one might be thinking about what distributional measures or other constraints would be a better way to capture these, in this case, clearly non-stationary input. But the idea, of course, to capture these transitions from T1 to T2 and so forth would be, of course, to kind of implement or recover or synthesize these non-stationary aspects at the same time. And it seems that the price data that are produced by the network, they do exhibit such patterns as well. Absolutely. To the extent you can see that with 24 time steps, right? I mean,
Yep. So Melissa has a question. Does this process necessarily produce synthetic data series which are smoother than the original training series? If so, how helpful are they for further analysis?
I mean, maybe it's a smoothness that's good because it filters out noise, maybe, right? So this you would have to investigate. Clearly, I would think that as an input for further work, we would something that really to regenerate the original series and not some, smoother that somehow is created by the network where we don't know whether that's desirable. So I would argue that scale and some modifications to the architecture may be ways to produce somewhat more realistic series. Right? The goal was to show that with a relatively simple setup, you do actually get quite some steps in those directions. Now, this is not the goal. This is the solution you should go with. We're done with we have solved the problem of synthetic data generation and finance, right?
Absolutely, absolutely. I think it kind of relates to the next question too, which is looking at the plots, the synthetic data generation was outperforming the real. Often the problem with ML in trading is that the results are as good as that of the data. Would it be possible that these networks could generate synthetic data that are not exactly compared to that of the real counterparts, but are generated in such a way to help identify parameters of interest in real data during forward testing? That's the question.
Can I actually read the question because that was a longer question?
Yeah. So I'll say that. So often the problem in machine learning in trading is that the results are as good as that of the data. Would it be possible that these networks could generate synthetic data that are not exactly comparable to their real counterparts, but are generated in such a way to help identify parameters of interest in real data during forward testing?
So the first part, are there shortcomings in the similarity or the faithful reproduction of the actual patterns over time? I think we've clearly seen that there are limitations, right? Which again, I would say, may very well be due to the limited input scale and other shortcomings of the architecture and the parameters and some of the constraints that it uses, right? So clearly, whether there are benefits of the specific data generated at this point that would sort of facilitate training or identify other aspects, I'm not sure. The goal of the embedding space is to capture sort of the relevant transitional dynamics in a smaller dimension. That has some value that would make it possible to begin with to scale kind of the exercise up to hundreds, thousands, or even more stocks, with also longer time series, right? Because you don't want to backtest a strategy on 24 time steps, right? So the whole, both in the time dimension and sort of the universe, things would have to be substantially bigger to be useful, right?
Absolutely, absolutely. Cool. So I think we are at 1:04. Thanks so much, Stefan, for spending your afternoon with us, or in the morning. You probably have one more hour to get to the afternoon. So
yeah, it's just noon, exactly.
I also want to, call out that if you are interested in experiments like these and other experiments, please do check out Stefan's book. It's algorithmic. So it's the really fat book, the second edition, Machine Learning and Algorithmic Trading, and his GitHub site has all the code associated with it. And on the page I shared with you, you have a link to Stefan's LinkedIn profile too, so please do connect with him if you have any questions. And we will look forward to having you back at the next lecture of the Quant University Fall School next week, talking about alternative data and how APIs are facilitating it. Thanks so much for spending your afternoon with us, and I wish you a wonderful rest of the week. Take care. Bye-bye.
Bye, everybody. Thank you.